Hello, listeners. Welcome to Deep Dive, the podcast where we venture into the unknown and unravel the mysteries of the universe, one topic at a time. I'm your host, Amy, and today, we're embarking on a cosmic journey filled with celestial dances, dramatic encounters, and the enigmatic forces that shape our universe. What if I told you that black holes and neutron stars engage in intricate cosmic waltzes that not only challenge our understanding of physics but also forge elements essential for life? Or that galaxies themselves are dynamic arenas where gravitational interactions can fling entire solar systems into the abyss of intergalactic space? Strap in. Because today, we're exploring how these mesmerizing dances begin. The origins of twin neutron stars, the unions of black holes and normal stars, and the extraordinary potential of intelligent life adrift in isolation. Let's start by unraveling how twin neutron stars come to exist and dance together in the first place. The story begins with massive stars. Stars at least 8 times the mass of our Sun, that are born together in stellar nurseries. These stars form in clusters where multiple stars originate from the same giant molecular cloud. Now, imagine 2 massive stars forming in close proximity, bound by their mutual gravity. A binary star system. Throughout their lifetimes, these stars orbit each other in a gravitational duet. Massive stars have relatively short lifespans, burning through their nuclear fuel rapidly. When the first star exhausts its fuel, it undergoes a supernova explosion, leaving behind a neutron star, a dense remnant composed mostly of neutrons. But here's the twist. The supernova can impart a kick to the neutron star, potentially disrupting the binary system. However, if the stars were close enough, their gravitational bond can survive this violent event, keeping the neutron star and its massive companion in orbit around each other. The second star then evolves and eventually also goes supernova, becoming a neutron star as well. If the system remains bound after this second explosion, a remarkable feat given the immense forces involved, we end up with a binary neutron star system. These twin neutron stars continue their cosmic dance, orbiting each other while emitting gravitational waves that slowly draw them closer. Over millions or billions of years, they spiral inward until they eventually merge in a cataclysmic collision. This merger releases an enormous amount of energy, including gravitational waves and electromagnetic radiation, and is thought to be a primary source of heavy elements like gold and platinum in the universe. Understanding how twin neutron stars form gives us insight into the life cycles of massive stars and the dynamic processes that can lead to some of the most energetic events in the cosmos. Now, let's explore how a neutron star and a black hole might come to dance together. This pairing is rarer and involves even more dramatic events. Similar to the formation of twin neutron stars, imagine a binary system where 2 massive stars orbit each other. The more massive of the 2 evolves faster and goes supernova first, becoming a neutron star or, if massive enough, a black hole. If the first supernova leaves behind a neutron star and the system remains bound, the second star will eventually undergo its own supernova. Depending on its mass, it could become a neutron star or collapse directly into a black hole. Alternatively, the initial mass difference between the 2 stars could be significant enough that the first star becomes a neutron star, while the second, being more massive, collapses into a black hole after its supernova. The key point is that both stellar remnants remain gravitationally bound, continuing to orbit each other. These neutron star black hole binaries are fascinating because they allow us to study extreme physics under conditions that are otherwise impossible to replicate. When they eventually merge, they produce gravitational waves and electromagnetic signals that provide valuable data about the nature of dense matter and gravity. Detecting such events has been a significant goal for astronomers, and in recent years, observatories like LIGO and Virgo have reported observations of neutron star black hole mergers, confirming that these cosmic dances do occur. Now, let's consider a more nuanced dance, a black hole paired with a normal star. A star like our Sun or even more massive. How can such a pairing exist without the black hole immediately consuming the star? This scenario typically arises in one of two ways. First, the stars could have formed together in a binary system, much like our earlier examples. One star evolves faster, ending its life in a supernova and becoming a black hole. If the explosion doesn't disrupt the system, the black hole and the normal star continue to orbit each other. Second, a black hole could capture a passing star through gravitational interactions, especially in densely populated regions like globular clusters or galactic centers where stars are relatively close together. In these systems, the normal star can survive because of the balance between gravitational forces and orbital dynamics. The star is in a stable orbit around the black hole, much like the Earth orbits the Sun. The key is the distance between them. If the star is far enough away, it won't be torn apart by tidal forces. However, the black hole's gravity can still have significant effects. It can draw material from the outer layers of the star if they are close enough, a process known as accretion. This material forms an accretion disk around the black hole, heating up and emitting X-rays that we can detect with telescopes. These X-ray binaries are crucial for studying black holes because they provide observable evidence of these otherwise invisible objects. The ongoing dance between the black hole and the normal star can last millions or even billions of years, depending on the rate of mass transfer and other factors. So, the delicate balance of gravitational forces allows a normal star to coexist with a black hole in a cosmic dance that is both stable and immensely informative for astronomers. Now that we've explored how these intimate cosmic dances begin, let's transition smoothly to the grand movements of entire galaxies and consider the implications for solar systems like ours. Our Milky Way galaxy is a vast collection of stars, gas, dust, dark matter, and of course, black holes and neutron stars engaged in various dances. In about 4.5 billion years, the Milky Way is set to merge with the Andromeda Galaxy. This monumental event will reshape the cosmic landscape on an unimaginable scale. But how do such galactic mergers affect individual solar systems, especially those located near the edges of their galaxies? During the merger, the gravitational interactions become highly complex and chaotic, particularly in the outer regions. Stars and their accompanying planets near the galactic edges are more vulnerable to these disturbances. The combined gravitational forces can alter their trajectories significantly. Some solar systems may find themselves catapulted into new orbits within the merged galaxy. Others might gain enough velocity to escape the gravitational pull of both galaxies entirely, becoming rogue systems adrift in intergalactic space. This ejection is more likely for systems near the galactic periphery because they require less additional velocity to break free. Could our solar system be among those ejected? While current models suggest we'll likely remain within Milkomeda, the new galaxy formed from the merger, the possibility isn't zero. Our position in the Milky Way is relatively secure, but the sheer scale of gravitational forces at play means that some unpredictability remains. Understanding these processes helps us appreciate the delicate balance that keeps our solar system stable and the potential cosmic events that could disrupt it. Imagine now a solar system that has been ejected from its galaxy, drifting alone in the vast darkness of intergalactic space. What would this mean for any intelligent life forms residing on planets within that system? At first glance, the prospects might seem grim. A night sky devoid of nearby stars could have profound psychological and cultural impacts on such civilizations. However, isolation could also be a powerful driver of curiosity and innovation. With fewer celestial bodies to study, any visible stars or galaxies would become objects of intense interest. This scarcity might inspire advances in astronomy and physics beyond what we can imagine. The challenges of limited resources and the absence of external threats like supernovae could foster a focus on sustainability and long-term survival strategies. Moreover, the stability offered by such isolation might allow civilizations the time needed to develop technologies for interstellar or even intergalactic travel. Without the frequent cosmic disturbances present in more crowded regions of space, these societies could pursue grand projects with less risk of catastrophic interruption. So, while being cast adrift in the cosmos presents significant challenges, it also opens up unique opportunities for growth and discovery. It's a testament to the resilience and adaptability that intelligent life might possess, regardless of its circumstances. Returning to our earlier analogy, the universe plays a complex game of pool, with black holes, neutron stars, and galaxies as the balls in motion. Every interaction, every gravitational tug or collision, changes the trajectories of these celestial objects, leading to new configurations and possibilities. Consider how a passing black hole might disrupt a star cluster, sending stars careening into new orbits or even ejecting them entirely. These events can trigger the formation of new stars or alter the evolution of planetary systems. The mergers of neutron stars and black holes don't just produce gravitational waves, they also forge heavy elements and disperse them across space. These elements become part of new stars, planets, and ultimately, life forms. In fact, the iron in your blood and the calcium in your bones were forged in ancient stars that exploded long before our solar system existed. This cosmic game of chance and chaos is fundamental to the evolution of the universe. It's a continual process of destruction and creation, where even catastrophic events pave the way for new beginnings. As we contemplate these grand cosmic dances and the forces that set them in motion, it's natural to reflect on our own place in the universe. Earth is a tiny speck in a vast cosmic ocean, yet we have the capacity to understand these immense phenomena. Our solar system benefits from a relatively stable position within the Milky Way, far enough from the galactic center to avoid harmful radiation and not so close to the edge as to be easily ejected. This stability has allowed life to develop and thrive on our planet. However, the future is uncertain. Events like the merger with Andromeda or the evolution of our Sun into a red giant will pose significant challenges. Yet, humanity has continually demonstrated an incredible ability to adapt and innovate. By studying the dances of neutron stars and black holes, we not only satisfy our curiosity but also gather knowledge that could be vital for our future. Understanding gravitational waves, for instance, could lead to advancements in propulsion or communication technologies that enable us to explore beyond our solar system. Ultimately, recognizing the dynamic nature of the cosmos inspires us to appreciate the fleeting yet precious stability we currently enjoy and motivates us to prepare for the changes that lie ahead. The universe is a grand tapestry woven from the threads of countless cosmic dances. From the intimate waltz of twin neutron stars to the colossal merger of galaxies. Understanding how these dances begin enriches our appreciation for the intricate processes that shape everything from the smallest atoms to the largest cosmic structures. Black holes and neutron stars don't just captivate our imaginations, they forge the elements essential for life, redistribute matter across galaxies, and challenge our understanding of physics. Galaxies merge and evolve, reshaping the cosmos and setting the stage for new stars and planets. And even in the vast isolation of intergalactic space, the potential for intelligent life to adapt and thrive remains. As we ponder these phenomena, we're reminded of the interconnectedness of all things. The gold in our jewelry, the stability of our solar system, and the potential for life in the most isolated corners of the universe. All are products of the same cosmic processes. Thank you for joining me on this journey through the cosmos. If today's deep dive sparked your imagination, don't forget to subscribe, like the video, and leave a review. Share your thoughts on these cosmic dances and how they inspire you. And remember, in the vast expanse of the universe, every one of us is part of a grand performance of existence. Until next time, keep exploring.